Okay, very good morning, Valinda. Today we can discuss the elements of PCM. Okay, so what we can discuss regarding the coding section. So in the last class we have discussed the sampling and quantization. Okay, so what is meant by sampling? It is a process of converting a continuous amplitude getting the continuous amplitude sample from continuous signal or from the analog signal. Okay, now how many types of sampling techniques we studied? We studied 3 different types of sampling techniques. Okay, so what are the 3 different types? Ideal sampling, instantaneous sampling, and last one is the flat top sampling. Okay, ideal or instantaneous, second one is natural, and third one is flat top sampling technique. So we discussed that we have like lot of advantages for flat top sampling because the pulses of flat tops, okay, if the pulses of flat tops are generated, then that kind of signal is very much compatible with the digital communication. Okay, so that's why we can consider flat top sampling because it is highly compatible to digital communication. Okay, so after sampling we'll have the quantization in order to convert analog signal to digital signal. So what is quantization? So the output of the sampled signal, if you consider it as a flat top sampling, okay, so the output of the flat top sampling acts as input to the quantizer. Okay, so in the last class we discussed different types of quantization techniques. So let us, what are the different types of quantization techniques we studied? We discussed 2 types. One is uniform quantization and second one is non-uniform quantization. And what is meant by quantizer? Actually, this quantizer converts continuous amplitude sample into discrete amplitude sample. Okay, so what it means actually, here you are converting the y-axis continuous amplitude into you are making it as discrete amplitude levels. Okay, so into how many discrete amplitude levels you can identify? You can extract 2 power n number of amplitude levels for the n bit sequence, Now, for example, if you want to generate a 4-bit sequence, okay, so then how many levels you need to divide? The quantizer divides 2 power 4, that is 16 number of quantization levels. Now, how many, in general, these discrete amplitude levels of the quantizer are generally called as representation levels or reconstruction levels. Okay, so what are the amplitude levels called as? Those are called as representation levels or reconstruction levels. Okay, now the spacing between those 2 representation levels is generally defined as step size. It is called as step size. So based on the step size, okay, based on the step size value, if it is fixed, it is called as uniform quantization. If the step size is variable, it is called as non-uniform quantization. So already we discussed these 2 points in the last class. So uniform quantization where the step size is fixed. What is step size? It is the spacing between the representation levels. Okay, so if the spacing between the representation levels is not constant or not uniform, then it is called as companding. Okay, this is about the classification of quantization. Now, so please tell me, already we have discussed this. Okay, please tell me, uniform quantization is classified as 2 types based on the origin location. Okay, that we have seen in the next slide. Okay, so in the last class we discussed all these things. Okay, so in the mid-rise, if you see, the origin lies in the rising position. The origin lies in the rising position of the staircase waveform. So in general, the quantization response will be the staircase graph. So how the graph looks like? It looks like a staircase waveform. Okay, now in the mid-rise, the origin generally lies in the middle of the rising part of staircase graph. Okay, now always remember that in the mid-rise, we don't have 0 level. Okay, 0 reconstruction level. Okay, because the amplitude levels will be like minus 3.5, like you will have 0.5 factor. Okay, but in the case of mid tread, the origin lies in the horizontal position or the tread position of the staircase graph. Okay, so it will have the representation levels like that range from minus n2 plus n, minus n2 plus n. Here we have zero reconstruction level. That is a basic difference between mid-rise and mid-tread. Okay, we completed this thing. And always remember that the quantizer response will be a staircase waveform with a like deviation as, with the deviation as how much? Step size, which is equals to delta. If you consider delta as 1 for uniform quantization, then the range frame is from minus n.5 to plus n.5. So like minus 3, if n is 3, you can consider minus 3.5 to plus 3.5 delta for mid-rise, and if for mid-tread it will be from minus 3 to plus 3. Okay, so this is about the classification of uniform quantization, and next we discuss the non-uniform quantization. So what is non-uniform quantization? So here we have the variable step size. Here we have variable step size. Okay, here the quantization error, always remember that quantization error is generally proportional to the step size. So that's why if the quantization error depends on step size, therefore our SNR will vary for various input magnitude levels. But what happens to the SNR then? SNR will change for low level magnitude and high level magnitude signals. So in order to generate constant SNR or uniform SNR, generally non-uniform quantization is considered. Okay. Now let us move to the next slide. So what is the basic difference between uniform and non-uniform? In uniform we will have uniform step size or fixed step size, but in the case of non-uniform, if you observe the graph, you can see for low level input signals you will have low step size, and for high level input signals you will have high step size. Okay, this leads to a uniform SNR. So non-uniform quantization generates constant SNR. Okay, this all things we studied in the last class. And how can you generate encoding? So for example, if you want to encode into a 3-bit sequence, in general the quantizer divides into 2 power 3 representation levels. If it is n-bit sequence, 2 power n quantization levels will be there. So if you observe the encoding graph, okay, please observe the encoding step here. What you are doing here, right side represents the quantization level that range from 0 to 2 power n, and for a n-bit sequence you will have 2 power n number of possible combinations, 2 power n number of possible combinations. That for example, if it is a 3-bit sequence, you will have 0 0 0 range to 1 1 1. So based on the amplitude value, the corresponding data will be encoded. So it means that the analog, for example, if you consider this as voltage, so right side magnitudes are nothing but the voltage levels of message signals. Now these analog voltages are converted into the binary sequence by using this encoder. Okay, so like that finally you generated a binary sequence which is in the form of code. Okay, code that is 0 or 1 sequence. Okay, so this is about encoder. Now finally the encoder generates the PCM signal, pulse code modulated signal. Okay, so now the output of the encoder is which is a PCM signal, is directly fed to the channel. Okay, once it is fed to the channel, our PCM signal may get distorted. Okay, so if the signal is distorted, then we can regenerate the original signal by using regenerative repeaters. Let us move to the next slide where you can see the regenerative repeaters. So we have so many number of regenerative repeaters in the channel. So I think up to this we completed it in the last class. let us once again revise. So the repeaters generally consists of three sections. One is amplifier section, second one is timing circuit, and third one is decision making device, and the third one is decision making device. Now if you observe the amplifier, this amplifier, what it will do, it will strengthens the distorted PCM, because once the PCM signal at terminal 1 is applied to the channel, the signal gets distorted. Okay. So generally if there is any frequency variation, the signal will gets distorted and the signal gets attenuated with whenever we have phase variation. Okay, that thing we studied in the analog communication. So always the phase distortion creates attenuation, and a frequency distortion frequency variation generates the distortion in the signal, distortion in time. Okay, now that distorted PCM signal, the magnitude is strengthened by using the amplifier section. Okay, now that signal is compared with the decision level. This decision level is nothing but the predefined threshold value. Okay, this value is generally a constant, like provided by the, it's a constant value which is a predefined value provided by the manufacturer. Okay, so the strengthened PCM signal is compared with the threshold, and the output of the decision making device will be 1 whenever the PCM distorted PCM magnitude is greater than decision level, and it is equals to 0 when the PCM signal magnitude is less than the decision level. So then what is the importance of this timing circuit? Timing circuit generally generates the synchronized pulse train at sampling intervals. Okay, this is all to extract the sampling intervals. Okay, extract the locations of sampling intervals. This can be provided by the PCM signal itself. Okay, so finally these repeaters which are present in the channel regenerates the original PCM component. Okay, this is all about the repeaters which are present in the channel. Now the PCM signal, recovered PCM signal obtained from the repeaters are collected by the receiving antenna. So the receiving antenna collects the data and sends to the receiving section. But the PCM, if you observe we observe the PCM block diagram. In the receiving section, it consists of decoder and reconstruction filter. So reconstruction filter, the example for the reconstruction filter is low pass filter. Why you are considering low pass filter here? Because our intention is to extract only the low frequency signal, because our message signal is a low frequency component. Okay, now please tell me what is the input to the decoder here? The input to the decoder is the output from the repeater section. It is a binary sequence. Okay, so you can observe the binary sequence, which is nothing but the regenerated PCM signal. Okay, these, please all of you carefully listen here. Okay, so this is a regenerated PCM signal which acts as input to the decoder. Okay, now this output that is applied to the make and connect samples. So nothing but this decoder section consists of what it will do actually. Here it will first collect the PCM signal, and then the collected n-bit sequence is divided into certain number of samples. Okay, based on the sample value, it will identify how many number of bits are there per frame, or like per sample. Okay, now if it is a for example here we consider 3-bit data, then what this decoder will do? Decoder divides the whole sequence into n number of frames. How many number of frames? N number of frames. For example, if it is a 3-bit data, it divides into a frame consisting of 3 bits. So what this decoder will do? Please always remember that this decoder divides the n-bit sequence into certain number of frames, such a way that each frame consists of n bits. Each frame consists of n number of bits. Okay, so what this decoder will do? Decoder divides the whole sequence into certain number of frames. Okay, certain number of frames based on the number of bits per sample. Okay, and then the particular frame value is converted into analog voltage. It is converted into analog voltage. So the decoder working principle is exactly opposite to the encoder. So what the encoder will do? Encoder converts the analog voltage. So nothing but the discrete voltage value into a binary sequence. Now what this decoder do? First decoder divides the whole sequence into n number of a certain number of frames that depends on n, and each frame consists of once again n number of bits, and then the particular n bit value, n bit sequence will be converted into analog voltage. Okay, and the same voltage will be hold. Okay, the same value will be kept hold till the next sample or next frame arrives. Here frame is nothing but the sample. Okay, and once again once for example, if the new sample is arrived, then what it will do? It will convert that particular sample value into analog voltage, and that voltage will be kept in hold till the next sample arrives. Like that, what it will do? It will take the particular frame value and convert it into, and it converts into analog voltage, and the same analog voltage will be kept in hold till the next sample arrives. Like that, this decoder converts the binary sequence into analog voltage, and the same voltage will be kept in hold till the next sample arrives. Okay, so you can observe the output of the decoder, which is in the form of PAM signal. Okay, so the output of decoder is nothing but a pulse amplitude modulated signal, because because in the pulse amplitude modulated signal, the amplitude varies. Okay, it is a flat top sample signal. So how the decoder converts? Decoder converts the binary sequence into, you can say it as a pulse amplitude modulated signal, because the this modulated signal appears in a form such that it consists of pulses of varying amplitude, and the pulses of varying amplitude in accordance with the message signal. So what is the conclusion here? Decoder converts the binary sequence into PAM signal. That's all. Now that PAM signal magnitude is reconstructed using the low pass filter. What this low pass filter do? Low pass filter reconstructs the message signal from the PAM signal. So the pink waveform represents the PAM signal, and that is applied to the low pass filter. So because low pass filter, you will have a capacitor in shunt. It will bypass all the high frequencies to ground, and only the low frequency components will be reconstructed, and that is set to the output section. So finally you will get only the low frequency component as the output of low pass filter. So because the this low pass filter reconstructs the message signal from PAM signal, it is called as reconstruction filter. Okay, so is it clear to everyone? So what is the importance of decoder and low pass filter here? So decoder converts, what is the first step of decoder? It divides the entire binary sequence into frames or into certain number of samples, such a way that each sample consists of n number of bits. Okay, and each frame value is will be converted into analog voltage. So final, and the same voltage will be kept in hold till the next sample arrives. That's why if you observe the PAM signal, you can attain flat tops, and these flat tops are according to the digital data. Okay, according to the digital data. Now finally the decoder which will make and connect samples. What it will do? It will make the analog voltage and connect all the samples to generate a PAM signal. So decoder converts the binary sequence into PAM signal. That PAM signal is reconstructed, okay, is applied to the reconstruction filter to generate the message signal. Because for a low pass filter you will have capacitor in shunt. Okay, so once we have capacitor in shunt, generally the capacitor allows the high frequency component. Okay, so that's why the shunt capacitor allows all the high frequencies to ground, and it transmits only the low frequency component to the output section. So that here the low pass filter is generally called as reconstruction filter, because it reconstructs the low frequency component from the PAM signal. Is that slide okay to everyone? One of you please respond.
Yes, ma'am.
Okay, ma. Okay, thank you. So what the decoder do? Decoder converts binary sequence to PAM signal. That PAM signal is applied to the low pass filter to generate analog signal. Okay, let us see the working principle using I have represented it in the form of steps. You can see it in the next slide. Okay, please observe this. So decoder followed by low pass filter. These are the following steps which I discussed till now. Okay, so what is the first step here? See, this is a binary sequence. So what is the binary sequence shown here? 110, 011, 001, 111. Okay, now this sequence is divided into certain number of frames. Here frame is nothing but the sample. You can replace the term frame with sample. How the binary, this is a PCM signal. This PCM signal, how can I say that this is a PCM signal? Because it is a binary sequence. Okay, here this is a binary sequence or encoded sequence. That's why I can say this as a PCM signal. Now this recovered PCM signal, which is in the form of zeros and ones, first it is divided into certain frames. How many frames we have divided? 4 frames, for example. And always remember that each frame consists of how many number of bits? N number of bits. N number of bits. And for example, here I assumed the number of bits as 3. So that's why I have divided the entire sequence into 3 bits per frame. 3 bits per frame. So how many frames you got? You got 4 frames, and out of that each consists of 3 bits. Like that, the decoder will first identify each frame in the data stream and extracts the binary numbers from each frame. So what it will do? The decoder first divides the whole sequence into certain number of frames, such a way that each frame consists of n bits per sample. So 3 bits per sample here. So after then what it will do? So opposite functionality of encoder, what it will do? The binary 3-bit binary sequence is converted into analog voltage. Okay, is converted into a voltage value. That voltage value is proportional to the binary number. Okay, so what is the voltage value of 110? Any one of you please respond. What is the voltage of 110? What is the voltage of 110 and what is the voltage value of it is 6. Yes. 011,
6.
011,
3.
3, and 001 it is 1 volt, 111 it is 7 volts. Like that it is divided into
1.
yes, 111 is 7. Okay, like that this the particular sequence is first converted into divided into frames. Each frame consists of n bits per sample. Based on the n bits, it is accordingly divided into 2 power n number of voltages. Okay, so if it is 3, 2 cube అంటే ranging from 0 to 7. Like that, analog voltage will be generated, and that is proportional to the binary number. Okay, now what is the next step? Finally, that analog voltage will be continued or kept in hold till the next frame is decoded. Okay, so this process is generally called as decoding. So decoding first divides the entire PCM signal into frames. Each frame consists of n number of bits, and then each frame value is converted into voltage that is proportional to the particular frame value. Okay, and then the same value will be kept in hold till the next frame arrives. Okay, so like that you can be able to generate PAM signal. So decoder directly converts the PCM signal into PAM signal. Okay, now that PAM signal is applied to the low pass filter for reconstruction of analog signal. Okay, this is about this slide shows the step by step representation of the earlier figure shown in the past slide. Okay, now this is about so finally up to this we can conclude that we have completed all the elements of PCM. So how many elements are there in the transmitter section? Low pass filter followed by A to D converter. A to D converter consists of sampling, quantization and encoder. Next, PCM signal you can generate, that is fed to the channel. Okay, so in the channel you will have more number of repeater circuits for regeneration of the in order to regenerate the distorted PCM signal. Now the receiving antenna somewhere located, it collects the distorted PCM signal, and once again it is applied to the repeater circuit to recover the distorted PCM. Okay, and the receiving section mainly consists of decoder and low pass filter. Okay, so PCM receiver section consists of decoder and low pass filter. What this decoder will do? Decoder converts the PCM signal into PAM signal, because it divides the entire PCM signal into frames. Okay, and each frame will be decoded, and the same analog voltage will be kept in hold till the next frame arrives. Like that, each frame will be individually decoded so that you can generate a PAM signal. That PAM signal is applied to the low pass filter in order to reconstruct the message signal. Okay, this is all about the PCM PCM elements. This is all about the elements present in PCM communication system. Okay, so next let us move to the next slide in order to identify the transmission bandwidth of PCM signal. See, already we have seen the PCM signal, and how can you identify the PCM signal? It is in the form of a binary sequence. I said you, it is in the form of a binary sequence in the form of zeros and ones. Okay, well and good. You have seen the entire communication system of, or the total block diagram of PCM system consisting of transmitter section, channel and receiving section. Well, but what is the what amount of bandwidth you need in order to transmit a PCM signal? Okay, so what sort of bandwidth you require for PCM signal transmission? How much of bandwidth you need to transmit PCM signal? So we can observe that from this slide. Please observe this slide. So what is the transmission bandwidth of PCM signal? For example, observe the first point. What is Fs? Let us represent Fs as the sampling frequency. Okay, so we have in the PCM signal, in the A to D converter, we have sampler section. So what this sampler will do? It divides the time axis into certain discrete intervals having a sampling frequency of Fs samples per second. So what is Fs? From the first point, we can say that let the sampling frequency be Fs. Okay, now, so what is the next step? Quantizer. So let us assume that quantizer has total of q number of amplitude levels. So how many representation levels we have? The quantizer divides the amplitude axis into q number of representation levels. Okay, for a n-bit sequence, for a n-bit sequence, let how many amplitude levels are there? Q number of amplitude levels. Now I can represent q as 2 power n because the quantizer always divides the amplitude axis into 2 power n number of levels. So I am defining here with a variable q. So what is q here? Q is equals to 2 power n. Okay, please always remember what is q. Q is the number of representation levels or amplitude levels. It is equals to 2 power n for a n-bit binary sequence. So always remember that what is n? N is a number of bits per sample or per frame. Per sample or per frame, how many number of bits are there? N number of bits are there. Okay, how many amplitude levels are there for the quantizer? Q, which is equals to 2 power n. That you can observe from the second point. Okay, now how can you define the signaling rate? Here we are defining a new term, okay, called signaling rate. So what is signaling rate? It is generally defined as the number of bits transmitted per second. It is also called as information rate. So what is this R here? R is, you can call it as signaling rate or information rate. So how can you define the signaling rate? Number of bits transmitted per second. See, every time we are speaking, how many number of bits are there per sample? How many number of bits are there per sample? N. How many number of bits are transmitted per second? R. You can say it with the signaling rate because signaling rate is nothing but the number of bits transmitted per second. What is the other name for signaling rate? You can also use with the term information rate. It is generally represented with a variable capital R. Okay, so signaling rate is defined as the number of bits transmitted per second. You can define it as the product of the number of bits per samples and the number of samples per second. Because if samples and samples gets cancelled, you will get bits per second as the unit for signaling rate. So how can you define R? R is the product of number of bits per sample and number of samples per second. So what is the unit for signaling rate R? Bits per second. What is the unit for N? Okay, N is the number of bits present per sample, present in a sample or present per frame. Sometimes you can replace this sample with frame. Okay, so how many number of samples are there per second? That is nothing but the sampling frequency. Okay, so final thing here is the signaling rate can be defined as the product of number of bits present per sample and the sampling frequency. See, you can call the number of bits present in a sample as the entropy. Okay, so what is signaling rate? Signaling rate R is defined as the product of number of bits per sample into, it's a product of number of bits per sample and the sampling frequency. What is N here? Number of bits per sample. What is Fs? Number of samples per second. That is nothing but the sampling frequency or sampling rate. Okay, so this is about the signaling rate. In general, the bandwidth required, okay, bandwidth needed for transmitting the PCM signal is equal to half that of the signaling rate. Okay, in general, the bandwidth needed is half to that of signaling rate. So what can be the bandwidth for PCM signal? So how much of bandwidth you need for PCM signal transmission? It is half that of the signaling rate. So nothing but R by 2. What is R? N into Fs. So you can say it as NFS by 2. But what is the relation between Fs and Fm to overcome the aliasing problem? Fs should be greater than or equal to 2Fm. Fs should be greater than or equal to 2Fm. So if you replace Fs as 2Fm, here N into Fm. So always the PCM signal bandwidth should be equal to NFS by 2 or greater than or equal to NFM. Greater than or equal to N into Fm, because you can define Fs as the sampling rate, which should be always greater than or equal to twice that of the message signal frequency component. So Fs should be greater than or equal to 2Fm. If you replace here, the PCM signal bandwidth is always greater than or equal to N into Fm, because Fs is greater than or equal to 2Fm. So 2 gets cancelled here. You have 2 in the numerator and 2 in the denominator. So finally, always the PCM signal transmission bandwidth is half that of the signaling rate. So you can define it as NFS by 2, or to avoid the aliasing effect, it should be greater than or equal to NFM. Greater than or equal to NFM. So let us recollect once again the derivation for transmission bandwidth of PCM signal. We are defining the sampling from the first point. We are defining the sampling frequency of Fs samples per second. From the second point, we are going to the quantizer. Quantizer divides the amplitude axis into, let us assume, with a variable q. Okay, so how can you define q? As 2 power n, as 2 power n. And now how can you replace q with n? You can replace it as 2 power n for a n bit sequence. Nothing but n is nothing but the number of bits per sample. How many number of bits are there per sample? You can also call the sample as frame. N bits per sample or per frame. Now what is signaling rate? Signaling rate is, the definition is, it is defined as the number of bits transmitted per second. How many bits, how many number of bits you are transmitting per second is generally called as signaling rate, or you can you can also call it with another term called information rate. Okay, so the signaling rate is generally the product of number of bits per sample and number of samples per second. So that's why you can, because once the samples and samples gets cancelled here, you will get bits per second. So what is signaling rate? Signaling rate is defined as the product of number of bits per samples and the sampling frequency. So R can be defined as N into NFS, with a condition that Fs should be greater than or equal to 2Fm. So what is the bandwidth required for PCM signal transmission? In general, the bandwidth needed for PCM signal transmission is equal to half that of the signaling rate. Half that of the signaling rate. Okay, so that's why what is the bandwidth? It is equals to R by 2 or NFS by 2, because R equals to NFS. But what is the relation between Fs and Fs and Fm? Fs should be greater than or equal to 2Fm to overcome the overlapping of higher frequency component with low frequency component. So PCM signal bandwidth is equals to R by 2 or NFS by 2, or it is greater than or equal to NFM. Okay, so this is all about the general introduction and the transmission bandwidth of PCM signal, as well as the each and every element present in the PCM. With this, we can conclude the third module. Okay, so is this module clear to everyone? Can we move to the fourth module? That is regarding the quantization error. Okay, so in the next module, we can be able to calculate the signal to noise ratio of PCM. Signal to noise ratio of PCM. Okay, that you can calculate by using the error. So in general, we will have quantization error. Okay, so first we can calculate the quantization error in order to evaluate the noise power, and then the ratio of signal power to noise power. Okay, normalized signal power to normalized noise power. You can calculate the SNR for PCM signal. Okay. Now, please one of you respond and tell me how many elements are there in a PCM signal, in a PCM system, how many elements are there? So, what are the elements present in the transmitter section? So, one of you respond and tell me how many elements are there in the PCM transmitter section? How many elements are there in a PCM transmitter section? Any one of you?
5, ma'am.
5. What are those?
Message signal and source signal, low
Okay.
pass filter, sampler,
Okay.
quantizer, encoder.
Yes. These sampler, quantizer and encoder can be combinedly called as Mire H1. Sampler, the process of sampling, quantization and encoding is generally called as?
A to D converter.
It is called as A to D converter. Okay, in detail if you want to say, PCM transmitter section consists of low pass filter and A to D converter. Very good. Next, any other student please respond. What kind of sections are required in PCM receiving section? What kind of circuitry is required in PCM receiver section? Any other student?
Ma'am, regenerative circuit, decoder and low pass filter, ma'am.
Regenerator, next decoder
Decoder, ma'am.
and
Low pass filter or reconstruction filter.
what is the importance of decoder?
Decoder, ma'am, it converts the digital signal into samples, ma'am. That
Into
means analog signal.
samples, nothing but the PAM signal. So
Yes,
that
ma'am.
can be reconstructed by using
By
the
using low
low
pass filter.
pass filter. Okay, very good. Okay, thank you. Next, any other student, please tell me how much bandwidth you need for transmission of PCM signal? Any other student? Any other student, please first you define the signaling rate and please define the bandwidth required for transmitting the PCM signal. So any other student, kindly respond and tell me what is the amount of bandwidth needed for transmission of PCM signal. Tell me in terms of signaling rate and tell me in terms of the message signal frequency. So meanwhile, I will share the module 4. Any other student respond? G0, ma G0.
Ma'am.
Can you tell me how much of bandwidth you require for in order to transmit PCM signal?
N into Fs by 2.
N into Fs by 2. In terms of FM, it is greater than or equal to N into FM.
2x.
Greater than or equal to 2F.
Replace, yes, N into 2FM divided by 2.
Equal to 2.
So it is greater than or equal to N into FM. Okay, ma, thank you. You can mute yourself. Okay, thank you.
Thank you.
Okay, ma, thank you. You can mute. Now, So in the we can continue this in the next class. Just I will give you the introduction to the module 4. In this module 4, we can calculate the SNR, signal to noise ratio, as well as the quantization error. Because how can you define the signal to noise ratio? It is defined as the ratio of normalized signal power to that of normalized noise power. Normalized noise power. Okay. So in general, the noise, so error present in the source encoder and channel encoder can be recovered because you will convert it into in the form of binary sequence. Once the sequence, once the output is in the form of code format, then you can be able to detect and correct the error by using various source encoding techniques as well as channel encoding techniques. Okay. But coming to the quantization, we have some sort of error present in the quantization. Okay. So this is to, we need to consider this quantization error because this quantization error depends on the step size. Depends on step size. We can see that in the derivation. Okay. So that's why it is very much important to consider the quantization error while evaluating the signal to noise ratio for a PCM system. Okay. So that's why we are going to evaluate first the quantization error and then we'll calculate the signal to noise ratio for a PCM system. Okay. So already we, please observe this slide. Already we defined the quantizer converts continuous amplitude sample into discrete amplitude sample. See here, why I represented x of NTS instead of x of t. Instead of x of t, generally the signal is represented in the form of x of t or y of t only because it is a variable with respect to time. But here because the sample signal is defined only at sampling intervals, that is NTS, that's why this input signal and output signal both are represented in the form of NTS. So x of NTS is the input to the quantizer, okay, where x represents the continuous amplitude sample. This is the output of sampler. Now this is applied to the quantizer. What this quantizer do? Quantizer discretizes the amplitude level. Okay, so you will get xq of NTS. Why I represented x suffix q? Q suffix q represents the output of the quantizer. That's all. Suffix q represents the output of quantizer. What that NTS represents? NTS represents that it is a sampled value. Time is discretized. Okay. Now here input is x of NTS and output is xq of NTS. This kind of notations will follow while calculation of quantization error and then the SNR. Okay. So in the so what is the input notation? X of NTS, which is a continuous amplitude sample. What is the output of quantizer? X suffix q of NTS, which is a discrete amplitude sample. Now, please observe the process of quantizing noise. Please observe the process of quantizer. How the response is? The quantizer response is in the form of a staircase waveform. What this Q represents? Q represents the process of quantization. Okay. So in the process, if you observe the graph, okay, x versus y, please observe the transfer function characteristics. X-axis represents the input, that is continuous amplitude sample, and y-axis represents the quantized signal, that is discrete amplitude sample. Now, what is xq of NTS? Xq of NTS is the output of quantizer and x of NTS is the input of quantizer. Please observe the characteristics. If you assume x as input and y as the quantizer signal, then y can be represented as q of x. Okay, and here we assumed the response as uniform quantization. That's why the staircase waveform is having a fixed step size. Can any one of you identify which type of uniform quantization is considered? Is it mid-rise or mid-thread? Any one of you? Is it mid-rise uniform quantization or mid-thread uniform quantization? Observe the characteristics and tell me. Mid?
Mid-thread.
Mid-thread. Okay, very good. So it is a mid-thread because the origin lies in the thread position of quantization. Okay, that's why it is called as mid-thread quantization. Now, how can you define the error? So when I can say that there is an error, we are transmitting some signal, and if we are not receiving the same signal, then I can say that there is some error. If the output is not the exact reproduction of the input, then we can say that there exists some sort of error. So that's why we have defined the quantization error as E, which is defined as the difference of xq of NTS and x of NTS. So what is quantization error? So error produced by the quantizer is generally called as quantization error. You can calculate that quantization error by taking the difference between the xq of NTS and the input of quantizer, that is x of NTS. Okay, so how can you define the quantization error? Difference between the output of the quantizer xq of NTS and input of quantizer, that is x of NTS. Now we are going to calculate the quantization error, which is xq of NTS minus x of NTS. Let us represent the quantization error as some E with the letter E. What is E? E of NTS is equals to xq of NTS minus x of NTS. Now any one of you please observe this graph, right side graph, and tell me which type of uniform quantization it is. Is it mid-rise or mid-thread?
Mid-rise.
Mid-rise. Mid-rise. Yes, yes. It's mid-rise only because the origin lies in the rising position. Now what is the step size here? Please observe the graph and tell me what is the step size. Step size is the difference between like successive representation level. What is the step size value there? Ma, what is the step size? Step size is the spacing between each representation level. You can observe the representation levels in the y-axis. So what can be the step size there? Each successive spacing level, please observe. 7 delta by 2 minus 5 delta by 2. How much? 2 delta divided by 2. So it will be delta only. So if you observe the difference between 5 delta by 2 and 3 delta by 2, it will be once again 2 delta divided by 2. So once again the step size is delta. So what is the step size here? Here step size, it is assumed as delta. It is assumed as delta. So because here it is a mid-rise quantizer, here we don't have zero representation level. Here we don't have zero representation level in the y-axis. Okay, so anyhow, this is the definition for quantization error, which is the difference between output of quantization, that is xq of NTS, and the input of the quantizer, that is x of NTS. Okay, so we can calculate first E of NTS and then we can substitute in SNR to calculate the SNR for a PCM signal, PCM system. Okay, so in the next class we can continue the derivation for quantization error. Okay, so any doubts in the today's session? Wait for a few minutes, I will take the attendance, then you can disperse. Any doubts in the today's session? Okay, we can discuss the derivation of quantization error and SNR calculation in the next class. So we can stop the session. I took the attendance. If no doubts, we can wind up the session. Okay, thank you. You can leave the meeting.